This is the 12.3 notes for statistics honors. In 12.1 and 12.2, we talked about inferences for one population proportion, specifically intervals and hypothesis testing. So similar to means, when we made the jump to comparing two means, now we're going to make the jump to comparing two proportions. So this one section 12.3 deals with both confidence intervals and hypothesis testing. We'll start with the hypothesis testing in a couple minutes. So just a note, just like we always start, we have the sampling distribution of the difference between two sample proportions for independent samples. So what is this all about? Well, if you remember, when we did the mean of the difference of the sample means, that was always equal to the difference of the population means. So now, same thing over here. If we take the mean of the difference of the sample proportions, it's going to be the same as the difference of the population proportion. So same thing, no big difference on what we're doing. Remember that the standard deviation of the population proportion is going to be some funky formula. It always is. But do remember that when we did one proportions, this guy should be very familiar with you in the square root. So now you can see we're just adding two of them within the square root. So not a huge deal on any difference. This is just preliminary sampling distribution stuff. So not a big deal, but that's kind of the idea. I'd rather just sort of tackle that when we get to it. Okay, so just based on what we've done in previous setups for our test statistics. So for Z, remember we're always going to do the difference of the stats minus the difference of the parameters over the big standard deviation of the sampling distribution. That's always the setup for all of these. So that's, if you look at the setup, that's exactly what's happening. So we have our statistics p hats, we subtract them, we compare it to our parameters, difference of our parameters, p1, p2, and then we have our standard deviation in the denominator. Always the same, but the key is what we do with this thereafter to find the actual formula. So just to be clear, the rest of this page right here is all about basically deriving the formulas that we're going to use. So just stay with me as we go. So again, remember in difference of means, what did we do? Our null hypothesis was mu1 equals mu2, right? Makes sense. It's basically the difference of them is 0. So once again, we're going to have the same setup, except instead of mu, we're going to have p's. So we're going to have p1 is equal to p2. So if that's the case, first one here, we of course know that if p1 equals p2, then this whole thing is equal to 0, which means our formula is only going to have this in the numerator when we get to it. So no change so far. Now, there's another byproduct of this, though. With p1 equal to p2, if you look at the formula at the top here, there's a lot of p1s and p2s in here that are all the same value. So if those are all the same value, then technically we can just drop their subscript. So if you look here, what I did is for all of these, I dropped the subscript and represented it as one variable, p. So we'll continue from there. If you look at this expression and this expression, they are the same. They are both hanging out in the numerators of their respective fractions, which means we can actually factor them out. Factor them out over here. So look at this, guys. So we're going to factor out this root 1, p1 minus p, and it's going to be left with this on the right side. This should be somewhat familiar to you. We had a lot of 1 over n1s plus 1 over n2s square roots, so when we were dealing with means, so it's not going to be a huge difference. But just like when we were dealing with difference of means when the standard deviations were similar or approximately the same, we basically came up with a pooled mean at the time, now pooled proportion now, in order to represent this value. But there is some logic to that, so I want to read that for you. It says, we do run into one problem though. The whole point of inference is to estimate the unknown parameter p. Therefore, we don't know its actual value. So when you're doing these problems, we're not going to be provided p. Whenever you do any difference problem, there is no parameter. So having a p appear in the front will not help us whatsoever. So what we did, basically what statisticians did, was they came up with something called a pooled sample proportion, similar to the pooled sample standard deviation that we came up before. They came up with a pooled sample proportion that we're going to be working on here to combine it. So what's the formula? It's p hat sub p, which is a pooled proportion, will be x1 plus x2. Remember, the x's in our values were the successes that we had, and then over n1 plus n2. So it's going to provide a happy medium for us for sort of not halfway necessarily, but sort of a middle point for the two sample proportions that we're going to find that are in the problem and provided to us. So in the end, we're going to end up with this as our big formula for calculating our test statistic. Okay, so let's talk about the two proportion z-test. So basically, I believe it's going to be 2 prop z-test in your calculator. So let's look at it all. So assumptions. Just like last time when we were doing means of differences, we have two random samples now that have to be simple, but they also have to be independent. We're only going to be covering independent proportion samples for this, just so you know. So that's going to be where we're going to be limited to. We also have the number of successes and failures for each sample. So this is success, fail, for all have to be 5 or greater. So just like I had the box over here, I don't have it this time, but I'm going to write it for you. So you should have n1 p hat 1 is greater than or equal to 5. We have n1 1 minus p hat 1 is greater than or equal to 5, and do the same thing for n2 p hat 2 is greater than or equal to 5. And n2 1 minus p hat 2 is greater than or equal to 5. So these are the ones that were in the box last time that I said sometimes you might want to use. Those are over here. I just got to add that at some point. It is another variation of the same thing. Just remember, we are using p hats for these because we have to. There are no p's that are given in our problems, regular p's as in parameter population proportions. So it's all going to be p hats that we're dealing with in the problem. So just like when we had our null was mu1 equals a mu2, we're going to have p1 equals p2, and then all the options thereafter for all the tailed tests. We already derived our test statistic, which is right here on the previous page that we'll be dealing with, and that is provided that this is our pooled sample proportion. Okay, so already covered this, so it's all about starting with an example. Okay, Zogby International surveyed 1,181 U.S. adults to gauge the demand for vegetarian meals in restaurants. The study commissioned a resource group and published it in a journal, pulled independent random samples of 747 and 434 men and women. Of those sampled, 276 and 195 men and women said they sometimes order a dish without meat, fish, or fowl when they eat it. Do the data from this poll provide sufficient evidence to conclude the percentage of U.S. men who sometimes order vegetarian is smaller than the percentage of U.S. women who sometimes order vegetarian? All right, so you'll notice that the difference of proportion problems have a lot of numbers in them. Why is that? Because we're going to have to come up with two different proportions in order to make this work. So normally when I start a problem, I always just find out what my p hats are going to be right in the beginning. So for example, p hat 1, which is our first sample proportion, we could also do p hat sub m for men if you'd like to, but the book doesn't do that. So again, I'm going to stick to what it does. If you look at the example, there were 747 men and 276 said they eat the vegetarian stuff, and p hat 2, which could also be p hat sub w for women, would be 195 out of 434. Okay, this approximately is 0.369. This is approximately 0.449. Okay, so that's pretty much the idea in terms of what we've been given in the problem. We also know that that's going to be alpha, but that's where we want to start. So we want to check our assumptions. So going back to our assumption setup here. So what do we need to do? We need to independent SRSs. So if you look here, I believe it said somewhere, it does, independent random samples right there. So we can do independent SRSs. So we're good. But we also have basically the need to check for normality. So normality is weird with proportions, just like it was in the one sample. It has nothing to do with looking at n bigger than 30 or anything like that. It's all about these little success formulas that we have. So in our problem, we are given the success values. They're right here, 276 and 195, so we can go ahead and use them. So we need x1, which is going to be 276, and we also need n1 minus x1, which is 747 minus 276, or 471. We need those to be greater than or equal to 5, which they are. Okay. Next, we need x2, which is 195, to be greater than or equal to 5, and we need n2 minus x2, which is going to be 434 minus 195, which is 239, I believe. Carry the 1. So all of these are way bigger than 5, so this ensures that we will have some semblance of normality in our problem, therefore we can move on and all assumptions are qualified. Alright, so null and alternative. What do we got? So we know that the null is a statement of equality. So what do we have? We have two proportions, P1 and P2, that we are hoping are going to be equal, or maybe not hoping, depends on the problem, but those will be equal. But our alternative has to be either not equal to, less than, or greater than. So right now, according to this, they're looking for, the key word here is smaller. So they think the men, which is represented by 1, and the women, which is represented by 2, they're saying 1 is less than 2. So P1 is less than P2, and we have a left-tailed test. All right, so what does that look like to us? Well, just like when we did the difference of means, we couldn't actually find the z-test statistic until we actually found the pooled value that is represented in it. So what do we need to do first? We need to find the pooled sample proportion. What is that the same as? That is x1 plus x2 over n1 plus n2. That is going to be equal to 276 plus 195 over 747 plus 434, which is going to give us, looks like 471, and this is going to be 1181. Which is approximately 0.399. Okay, so this is our pooled sample proportion. So just to be clear, if you look at this number right here, you can see that it is a nice sort of middle ground between the two individual p-hats. So we use that in our denominator for our z-test. So what does that z-test look like? So we have z is equal to, I'm going to write out the formula to start, p-hat1 minus p-hat2 over. In the front, we have our pooled proportion times 1 minus our pooled proportion, all in a radical. And then we have 1 over n1 plus 1 over n2, just like we had for means in the next radical. So this is our formula that we will use in order to find our z. So let's start subbing in some values. So we got 0.369, which I'm getting from here, minus 0.449, which is I'm getting from there, Okay, obviously we can use the fractions if we want to, so we don't have error in our problem. Obviously, if you're running a professional test, that's what you would do. But this can get very hairy, this calculation, if you start putting fractions everywhere. So I usually just tell students round to 3 or 4 decimal places and kind of call it a day. So in the front here, what's different? We're now taking this value in our formula. And then over here, we're doing 1 over our sample sizes. So our sample sizes are 747 and our end 434. We're doing it. So this is already crazy. So can you imagine having all of these decimals up top here all have their own fractions? Yeah, it's pretty nuts. But at least this saves some time for you. So you get, I think it's going to be negative 2.71 approximately as our value for our test statistic Z. Okay, as always, we're at that time. Critical value and p-value approach. Thankfully, have not changed, and they haven't since the beginning. I tend to go towards the p-value approach only because it is, to me, a lot easier. You will need to do both for your exams, so you need to do both in terms of, practicing, but we've done a lot of this practicing so far, so I'm sort of going to stick to the p-value approach for these guys. So we have to make a decision on our claim. Remember that our value was z equals negative 2.71. So very simple. We can throw that in our chart. Remember, this is a left-tailed test. So just looking at it here, remember this is left-tailed. So all we care about is this area right here. And this is going to be our p-value. So we can look up negative 2.71 in our z table. So let me get rid of old stuff here. So negative 2.71 is going to be here and here. So if we go and meet in the middle to try to figure out this value, it looks like we're going to end up with 0.0034 as our 0034 as our value. So what are we comparing this to? If you recall, we made a note that alpha was 5%. So we know that 0.0034 is less than alpha equal to 0.05. So what do? As always, we reject H naught. Okay, you already know how to do all the setup for that when it comes to filling in our little charts that we have in our lessons. But what does that mean exactly? So they rejected H naught, which means they're saying for sure that men order vegetarian less than women do. So that's the result of the test, at least for this scenario. And of course, just as a side note here, if we want to find this p using the calculator, we can do normal CDF of negative 1e99 to negative 2.71 with 0, 1 because we're dealing with a standard normal distribution. So we can do the same calculation in order to find that p-value. All right, so let's do another example. Number 1 says study of 150 randomly selected occupants in passenger cars and 200 occupants in pickup trucks showed that 86% of passenger cars and 74% of pickup trucks wear seatbelts. By the way, those are numbers that are low and make me sad. Side note, at alpha 0.10, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passengers and pickup trucks? Assume occupants are independently selected. All right. So again, what do I usually do first in these problems? I usually find P1 hat and P2 hat. So we got, let's go over here. So P hat 1, which could be P hat 1 passenger of some kind. I guess you can't do P because that's pooled proportion, but we're going to use 1. They actually give you it outright, 0.86. Okay. So what do we do with P hat 2? They also give that outright. That's 74. So that's the pickup trucks that are going on there. So the thing is, if you're looking at our sample, it's a little bit different. So last time we had to calculate P hat 1 and 2, but this time they gave it to you. So it's a little bit different, obviously. So what do I usually do next? I usually find, since we're running a test here, we got to do some assumptions. So it looks like they mention independent and random. So we got independent SRSs. But we also have all the checks. Now, note, remember up here what I was talking about? So same thing as last time. So we used these in the previous problem because we were actually given our x's, right? So in this problem, we're actually not. We're actually given, whoa, going too far. We're actually given the sample size and we're given only the proportions, which means this is the ideal place to go in order to figure out these requirements. So what does that look like? So we want n1 p hat 1, which is going to give you, we got 150 passenger cars, of which 86% are wearing seatbelts. So that's 129, which is bigger than 5. We got n1 1 minus p hat 1, which is going to be the same 150 minus 1 minus 0.86. That is going to give us 21, which is greater than or equal to 5. We're actually getting pretty small there. And note, sometimes you will get pretty small, and sometimes the test will be violated, and you're not supposed to do it. It does happen, and because of the lack of normality. So what about the next? This time we're given 200 pickup trucks. So 200 pickup trucks times 74%, which are wearing seatbelts, 148. Greater than 5, and then lastly, n2 1 minus p hat 2, 200 1 minus 0.74, which is going to give you, I believe, 52. Okay, so this whole thing allows us to determine this one down here. This allows us to determine normality, and we have. So therefore, we can move on and go to our test. So null and alternative. Null is always P1 equals P2. In other words, the passenger car and the pickup trucks wear the same proportion of seatbelts. In terms of the alternative, I'm going to read it. It says, can you reject a claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks? So when they say that, they're basically not mentioning anything about greater than or less than. So that means we're going to be in two-tail world, not equal to. All right, so as we spoke about before, we can't actually find z yet. We first have to find our pooled proportion. So what does that look like? That is x1 plus x2 over n1 plus n2. Okay, that's our value. But we do have a slight issue for this. So we actually don't have x1 and x2 right now. That's our sort of our hang up on what we have to do here. So we probably should find that right away. A little trick though, which is pretty neat, is believe it or not, even though we don't have it in our original problem, we actually did calculate it. So if you go back to here, this number and this number are actually our successes, our x's. So this is x1 and this is x2 in our problem. So by just checking the assumptions, we actually can find x1 and x2. So we're going to get 129 plus 148 over our 150 plus 200, which is going to give us approximately 0.791 as our pooled proportion, which is somewhere in the middle ground of 0.86 and 0.74. So yeah, you could have found these to begin with. So obviously, if you want to find the number of successes, you multiply the proportion times how many people there are. But it's nice that once you calculate the assumptions, you're basically finding x1 and x2. Okay, so let's find our z. So what is our z? We take our two proportions, 0.86 and 0.74 in the numerator. Then in the denominator, we have our two radicals. Our first radical deals with our pooled proportion. Okay, our second radical is going to be 1 over our sample sizes, which are 150 and 200. If we find this value, we're going to get approximately 2.73. Okay, so we can then move on and do our test. So this is a two-tailed test. I'm going to stick to p-value again. So we got 2.73 up here, which means we have a tail area, but because it's two-tailed, we also have a shadow symmetric tail area over here we need to compute. So we want to find this value, so we're going basically, either way we want to do it, it doesn't matter. So if you want to use the chart more effectively, then you probably want to take 0.273 and look that up, negative 2.73, because you know the chart goes to the left of everything. So you could just go, okay, 2.73, which is here and here, which means if we go in, we get 0.0032 right away, which means we know both of these are 0.0032. So the p-value is equal to 2 times 0.0032, or the sum of them, and get 0.0064. We're dealing with alpha 10%, which is pretty high, so we have, right now we got 0.0064, which is clearly less than alpha 0.10. So we reject H naught. In rejecting H naught, we go back to our hypothesis, and we can clearly see that we're saying that the proportions who wear seatbelts in these two cars are clearly not the same. Okay, it makes sense that our last stop in this section, and actually the chapter, is going to be our confidence interval for the difference between two proportions. In the calculator, it'll be 2 prop z int. So if you look at our assumptions for said interval, it will be the same as the test. If you look at the interval is set up the same way that we have for all the intervals that we've worked with. Especially if you go back to the difference of the means, this is the difference of the means here. Now it's the difference of the proportions, sample proportions. We're still going to have our value of z sub alpha over 2. It was t sub alpha over 2 in the means, but now proportions means we use z. And then this is always going to be the standard deviation of the sampling distribution, which is, again, what we did on that primary page, the first page that we went through in this section. So that is going to be the setup. You're going to find that I'm not going to do a lot of interval examples from here on out, just because it's a very straightforward concept of plugging in numbers. You'll get your practice when you're doing your my math lab, my stat lab stuff. All right, so let's go back to the vegetarian problem. We had this many men that ate vegetarian and this many women that ate vegetarian. This would represent our proportions. So remember, p hat 1, 276 out of 747, and p hat 2 is 195 out of 434. We're obtaining a 90% confidence interval for the difference p1 minus p2 between the US men and women who sometimes order vegetarian. Okay, so we already did the assumptions previously, so you would obviously need to check those assumptions again. So you would have to do, for example, 276 is bigger than 5, 747 minus 276 is bigger than 5. We just did that 2 examples ago, but you would have to do that in an interval if they requested it. So what do we do with any interval? We always talk about the confidence to start, which means alpha is 1 minus the confidence, which is 0.10, which means alpha over 2 is 0.05. Okay, from there, we should be pretty good in terms of using the formula. It's very straightforward. So what do? I'm going to, instead of rewriting it, since it's nice pushed together up here, I'm just going to use this as the guide right here and write it out. So we got, just as a reminder, by the way, this is 0.369 and this is 0.449. So we're going to use that. So our interval is going to be, it's pretty long, it's going to be 0.369 minus 0.449 plus or minus our z sub alpha over 2. So that's going to be z sub 0.05, which is going to give us 1.645. Remember, this can be confusing sometimes. So remember, this is in the t table at the bottom. So let me get rid of this. So z sub 0.05 is located right here, 1.645. And then we just have to do the big calculation over here. So we have p hat 1, 0.369, 1 minus 0.369, all over n1, which is 747, plus, on the other side, 0.449 times 1 minus 0.449 over 434. Okay, so lots of, just be really careful with the calculator when you're doing this. You're going to get negative 0.08 plus or minus 0.049. So that's this whole thing. So just a note here, on the left side, we actually have a negative answer. So students sometimes can be a little confused by this, but you are going to get a negative answer if P1 is smaller than P2 right off the bat, and it is. So it's not always, and that's not a bad thing. All it's doing is when we come up with the interval in the end, we're going to know that our first value is less than our last second value. So when we do the calculations, plus or minus, we're going to get negative 0.129 to negative 0.031. Okay, it's a little confusing because we're actually going from a smaller negative to a bigger negative, so it looks sort of out of whack, but realize this is exactly the type of interval you want. If you see an interval that's all negative like this, then you know that whatever the first sample we're dealing with is, in this case men, then that is going to be a lower proportion across the board than women in our scenario. So it's interesting, and I guess that's kind of the setup when we're dealing with these types of problems, but it's just about understanding what you're reading. If this interval was positive, then that means the proportions for men across the board would be bigger than women. That's all it's going to be. Okay, so last thing here. I'm not going to read it, I'm just going to explain it here. So if you remember, towards the end of each one of these sections, I always wanted to make a connection between intervals and tests in terms of using a confidence interval to make your decision about a hypothesis test. So I just want to point out that we cannot do that here. Why? If you go back to the test that we did for the vegetarian business, it was a left-tail test. Or in other words, generally just a one-tailed test. It wasn't two-tailed. Which means we cannot use this interval to make a judgment about that test like we have before. We can only do it if it's a two-tailed test. I wanted to point this out only because we had done it so often and we always were able to do it. So why not give you an example right now when we wouldn't be able to do it? And by the way, you might try to use it and come up with the right conclusion, but it's actually faulty logic. We can only use an interval because it's a two-tailed test. So don't try to do that in this problem in terms of the logic. It can only be two-tailed.